So the next part of this lecture, and probably what we'll finish up with today, is D'Alembert's solution. Okay, and the recorded lecture that I'll do, I'll show this in more, or I'll build on what I talk about today. So the idea is that we can show that, and this is sort of based on the example that I talked about last week in the recorded lecture, that this PDE, okay, without worrying about these initial conditions, is satisfied, okay, by u of xt is equal to some function f of x minus ct plus g of x plus ct. And in particular, if we want this to be a classical solution, we should need these functions to be what?
In C2.
Exactly. So we need them to be in C2 on our X domain, right? And on our T domain here, okay? And so in order to show this, right, we can just say, well, take this PDE, right? And we can write d dtt of u, that in this case would be equal to c squared f prime prime x minus ct by the chain rule plus c squared g prime prime x plus ct. And this is equal to c squared f prime prime x minus ct plus g of x plus ct prime prime, okay, which is equal to c squared dxx of u, okay. So indeed, it checks out. That works as a solution. So this should be fairly reminiscent of the transport equation, right? And what we can show is that you can actually separate out the operator for this PDE into just two different transport operators that are going opposite directions. So that's the intuition for why you have sort of counter-propagating waves, because this is really just like two transport equations kind of put together, okay? And so just to kind of tie this all back together, okay, x minus ct equals, well, maybe just use some of our language from before, s, and x plus ct equals s, which this is a constant, right? These are characteristics, right, of our PDE. And just for brevity, I'll refer to that as star, okay, later on. Also, if I take this operator now, okay, and write it like this, right? So this is also equivalent to that, right? But notice that I can write that operator, I can pull that operator apart as dt minus c dx and dt plus c dx, okay? So if I apply this operator and then I apply this, or if I apply this operator first and then I apply this operator, that's the same as just applying this operator here, okay? So the reason that's interesting, okay, sorry, I should write out the whole thing. The reason that's interesting, right, the fact that we can realize that this operator is equivalent to these two operators applied in succession, is that we note that when I apply this operator to just G, so G of X plus CT, then I get C times G prime X plus CT minus C times G prime X plus CT equals 0, right? So this part of the operator takes care of this part of my solution, right? And dt plus C dx acting on f of x minus ct, well, that's going to give me minus c f prime x minus ct plus c times f prime x minus ct, which is equal to 0, okay? So the different characteristics correspond to these two different parts of our solution, which in turn correspond to these two different parts of our operator that we can separate out, just like we would, like a quadratic polynomial. Okay. So in general, this is going to be our general solution to our PDE. That's D'Alembert's solution. We basically take that and we incorporate initial conditions and boundary conditions in order to build a solution to a particular scenario that we might come across. Okay. So u of xt equals f of x minus ct plus g of x plus ct is the general solution to that PDE, right, star. And it's essentially the superposition of two waves, right? We've already discussed the transport equation before. Each of these two parts of our solution is just a wave going in opposite directions, right? One of them's going to the right, f of x minus ct, assuming c is positive. And one of them's going to the left, g of x plus ct, okay? So you think of, f flows this way, and this is not exactly how it works. And then, g flows this way. So any initial displacement is going to propagate outward, just like, throwing a pebble in a pond, you get waves in all directions. Okay. So we get waves in both directions, okay, in the wave equation. Transport equation just had one direction, okay? And if we recall, right, from the lecture that I recorded for Friday, if I write this variable xi as x plus ct and eta as x minus ct, this converts star to d eta d xi u equals 0. Okay, so where I have this function now u of xi and eta. Okay, so what that means is du dxi is equal to g of xi if I just integrate this up with respect to eta. If I integrate this equation up with respect to eta, I'll be left with d dxi of u on the left-hand side and some function of g of xi on the right-hand side. Because g of xi, if I differentiate it with respect to eta, then I just get back 0, right? If I integrate again, then I get that u of psi eta is equal to some function capital G of psi plus f of eta, okay? Which is exactly what I have, and G here is just equal to the integral of G of psi, okay? So this again is just showing us that indeed we can write u of xt as capital U of x plus ct, x minus ct, or in other words, just f of x minus ct plus g of x plus ct, okay? So that's our general solution. That's D'Alembert's solution, okay? Let's apply it to an initial value problem, okay? And then I think we'll probably be done for today. So the initial value problem is like the one that I wrote down earlier, right? It's just our wave equation on r and t greater than 0. We have some initial displacement, which I'll call phi. And we have some initial velocity, which I'll call psi, okay? And this is defined on x and r, and I'm going to call this whole equation dagger, okay? So the general statement of D'Alembert's solution is that if phi is in C2 and if psi is in C1, the unique solution to dagger, okay, is given by u of xt is equal to a half phi of x plus ct plus phi of x minus ct, okay, plus 1 over 2c x minus ct x plus ct psi of y dy, okay? So that's our general solution. I'm gonna write this again on the next slide because I sort of ran out of room there, okay? So I'll rewrite this theorem and then I'll prove it. I think it'll last, it's just a calculation to prove it. Okay, so let me rewrite this. So if we have our theorem here, right, is that if phi is in C2 and psi is in C1, the unique solution to dagger is a half phi of x plus ct plus phi of x minus ct plus 1 over 2c integral from x minus ct x plus ct psi of y dy. Okay, so what's the proof? We just plug it in and check, okay? So first of all, our initial conditions, okay? U of x0 is equal to phi of x, okay? That should be equal to, right, f of x plus g of x, basically from before, okay? Remember our expression for the solution from before, okay? U sub t x0 is equal to phi of x. So that's equal to minus c f prime of x plus c g prime of x, right? This needs to be equal to psi of x. So again, this is just plugging in the general form of our solution. And we're going to back out what the form of f and g is from this, okay? So if we integrate the formula that we just derived, Then we end up with minus f of x plus g of x is equal to 1 over c integrated from 0 to x, phi of y dy plus a. Okay, so that's me just taking this formula or this equation here, integrating with respect to x, dividing by c. Okay, and as a result, I get this, and this a is just some constant, right? So now we're going to put this together with this equation here, and we'll solve for f of x and g of x. So I can solve for f of x by subtracting this formula from this formula and dividing by 2. And doing that, I end up with f of x is equal to 1 over 2 phi of x minus 1 over c integral from 0 to x psi of y dy minus a. If I take this equation and I add it to this equation, I end up with, and divide by 2, I end up with g of x equals a half phi of x plus 1 over c integral from 0 to x phi of y dy plus a. Okay. So then I remember what u of xt is, right? U of xt is just f of x minus ct plus g of x plus ct. So I get that u of xt is equal to f of x minus ct plus g of x plus ct. And when I plug this in, and then I combine these terms on the right-hand sides of these two equations here, I end up with a half phi of x plus ct plus phi of x minus ct plus 1 over 2c integral from x minus ct up to x plus ct psi of y dy, and the a's cancel out. Okay, so this is what's called D'Alembert's formula. Okay, and it was derived in 1740. Okay, so a couple minutes over, but before we go, I just want to think about why does phi and psi have to have this level of continuity? And why in particular does psi only have to be C1?
I think it comes from f and g having to be C2, right? So the antiderivative of psi has to be C2.
Yeah, so you can take care of one differentiation because it's shrouded in this integral, but you have to be able to differentiate psi at least once. Okay, so we essentially need that u needs to be C2 in this case. Okay, and even if phi and psi are less regular, you can still write down typically like a weak solution. So maybe one that's not differentiable everywhere. Okay, sorry to go a bit late. Are there questions about this? D'Alembert's formula?
I had a question about the first half. On
Sure.
the prelim, will we have to derive any PDEs from first principles, or is this just a homework and in-class thing?
Yeah, I mean, it's mostly just an in-class thing to give you the physical motivation. So yeah, I mean, if you look at exams and prelim problems, it's mostly about, for the wave equation, we'll talk about uniqueness from energy methods, solving the wave equation, maybe a little bit on like other aspects of well-posenness, but yeah, I mean, deriving PDEs from physical principles, that's, yeah. We want to motivate them in class, but yeah, it's not really something we test on for the most part.
Cool.
Other questions? Okay, so I'll send out an email just about where we'll have the in-person thing. I think it's supposed to be warmer on Friday. I'm thinking probably there's a field by the engineering building. If you want to come, you can. We'll try it this week. If you want to, bring a camp chair, and we'll have like a recitation session in person outside. If you don't feel comfortable coming, it's not obligatory or anything. I'll still record the lecture, but I'll send an email out about where to meet probably tomorrow, and yeah, and let you know if anything changes depending on the weather. Probably today would not have been a good day for it, but I'm assuming Friday will be better. So assuming that, I'll maybe see some of you in person on Friday over by the engineering building. See ya.
Thanks, Zach.
Yep. Thank you all.